Thanks for coming out to talk. This is bringing a 45-year-old CPU to life with Elixir and some LiveView. And if you don't know, this is the 6502 chip. It's a CPU. And I'm going to go a little bit into the history of it and about how I emulated it in Elixir in this talk. So first thing I'm going to do, I'm going to kind of start backwards and show the results first, which typically you don't do, but I'm going to do that. So hopefully this will, oh yeah, I forgot it's on that screen. Hopefully this will allow you to see, kind of have a visual of things as I'm going through how this is done. So this is the end result, and you can see on the left side there's some registers, some more numbers, and I'll go over all the details of that here shortly. On the right side you see a memory dump of everything that's in the memory right now on the CPU on my computer. And at the bottom we just kind of have my, my computer screen. And so you can see here if I run full speed, it's got just like a beginning OS type situation. So I'm going to stop that. I'm actually going to reset it, and we're going to come back to that later. But that's kind of what we're aiming for here in this talk, and that's what I wanted to get to. So the question that some people might have, if you're in this talk, you may not have this question because you're like, yeah, this is cool, but most people will be like, why do this? And so this is a bit of kind of a warning to everyone, to all developers who are of the nerdy sort as I am. All I wanted to do was make music when this thing started. So I'm a modular synthesizer nerd, so I like modular synthesizers. So I was like, I'm going to make my own module. So I coded one up on Arduino and put it together, and it worked, and it was cool. And I was like, I want to make another one, and it wasn't fast enough. So I was like, well, I want it to be faster. So I looked into how to make Arduino code faster, and I was like, well, use assembly language. So I was like, okay, cool. I need to learn assembly language. And so I started looking into assembly around Arduino, and I was like, man, this is really complicated. I don't know assembly at all. I have no experience with assembly. What's like an easier assembly to get into? And I discovered this 6502 chip that is kind of older and had a reduced instruction set, and it was well documented, very well documented. So I was like, okay, cool, I'll check into that. So I started looking into emulators, and all these emulators were for specific systems, like computer systems, and I just wanted the chip itself, so I could kind of build my own computer around it. And I couldn't really find a good emulator for that, so I was like, well, shoot, I'll just develop my own. And so that's where we are today. That's how I got here, is because I wanted to make music on my synthesizer. So the first part of this talk is going to be basics of 6502 and how hardware kind of works. And then the second half is going to be kind of transitioning from like hardware, bits and ones and zeros and wires, into making that work in Elixir. And a couple of, I guess, disclosures is I am not a 6502 nerd. Like there's people in here who know this chip better than I do, I guarantee it. This was new to me. The whole purpose of this project was for me to learn how the 6502 works. I'm not really a hardware guy. I kind of want to be a hardware guy. So that, again, is exploration of this. And also, I don't know how to write an emulator. So I didn't really go into this and like, I'm going to write an emulator, so I'm going to discover how people write emulators and the right ways to do things. I just decided to do it. And so there's, I'm sure, better ways to do some of this stuff I'm going to show you today. So if there are, please let me know. I'd love to make this better and release this and let you use it as well. OK, so 6502. It is an 8-bit processor. It was introduced in 1975, so it is over 45 years old. And at the time, it was like 1/6 of the price of the major competing processors at the time. So that was like the Intel 8008 and the Intel 8080. And when this came out, it really started a kind of a revolution in computing, especially like homebrew computing, and eventually moved into some of the many popular computing systems of the early 80s, mid 80s. And you may have heard of some of them. First, like the Nintendo Entertainment System had one of these chips in it. You had the Apple IIs, the line of Apple IIs. You had some Ataris. You had the Commodore 64. You had the BBC Micro. There was the Atari Lynx, like a handheld thing that had the 6502 in it. And so you might ask, well, that's neat and all, but it's an old processor, probably irrelevant these days. Incorrect. It's still produced in the hundreds of millions of units per year, which blows my mind. This 45-year-old CPU is still produced in such large quantities, and estimated in the wild 5 to 10 billion units out there. So if you really want to dig deep into this, it's possible you can find a job writing 6502 assembly, move from Elixir into 6502 assembly. And it's still a great hobby CPU. There's communities out there that build computers themselves, attaching all those wires specifically around a 6502 and some of its other components, which is pretty cool. So the architecture, what makes up the CPU? First of all, there's registers. So there's the A register, which is an 8-bit register, and that's typically called the accumulator. And so when the processor does an operation, it typically restores the results in the accumulator. And you can specifically restore things in the accumulator yourself, but like if you do like an AND or an or you're trying to move things from memory, it typically goes into the accumulator, and then you can move it around to other parts of the system as you need. There's also two other index registers, the X and Y index registers. Those are also 8 bits. Then you have P, which is an 8-bit status register, and there's 7 1-bit status flags in that register that typically tick on or off based on the last result of the operation you just did. So whether it caused an overflow, or maybe it's a negative result, or it's a 0 result. Those are different flags that the processor can flip on and off based on the result of the last operation. And finally, there's a 16-bit program counter. And that, as it kind of sounds like, it kind of counts through the program that you've given it. It steps through your program as it goes. All right, so it has stack and memory. So the stack register, or the stack rather, memory stack is hardwired. It's 256 bytes, but it's hardwired from the memory addresses of 100 to 1FF hex. And so that comes into play a little bit when you're trying to design a system around, trying to figure out how you're going to split up memory. That is hardwired by the chip, so you can't really do anything in there. So because it's 16 bits, you're able to access over 65,000 different address locations, memory locations. And when you're designing a computer, the allocation of those memory addresses are up to the computer designer. And so you can choose to whether you want all that to go to ROM, or you want half of it to go to ROM and half of it to RAM, or maybe if you're designing something in a factory, you need a lot of inputs and outputs, so maybe that like half of it goes to I/O, so controlling a robotic arm or something like that. It's up to the designer of the computer. And the exceptions are that memory stack I mentioned earlier. That's hard-coded. And also there's, at the very top or bottom of the memory range, whichever way you want to look at it, there's some reserved areas for reset vectors and interrupt vectors. And we'll go into a little bit of that later here in a minute. Someone's calling in. They want to hear my talk too. All right, so memory maps. What's a memory map? So when you're dealing about hardware, and especially these old types of CPUs, it's basically the layout of how memory is used, and the map, really. So you would take this map and be like, okay, well, I know, like, again, half of it's ROM, half of it's RAM, and you can use those memory locations because of that. And that's how the same CPU can be in different computers and be vastly different. So that's how it could be in a handheld device, and also like a general purpose Apple II, and also like a very dedicated gaming computer like the Nintendo. All that's because of the way the memory address locations are handled and all that. So again, it specifies the split. Here's an example of the Apple IIe memory map. So this is directly from the Apple IIe manual. And it showed, like, manuals back then, geez, this is an awesome manual. If you guys want to know how to do technical writing, this thing is amazing. But this basically shows how address is split up. So it has this addressable range, and it's like, well, you can see between 0000, no, that's 5. 000, no, that's 4. 0000, the 0, all the way up to BFFF. That's the main RAM. So that's your not read-only, but you can change those pieces of memory. Then you've got a little section there for I/O, things like keyboard and disk drives, things like that. And then you've got ROM, and then you also see there's like a bank switched RAM. So since there's not a whole lot of locations for memory, sometimes they would do these tricks where they would, based on like the particular value of a specific address location, you could switch over to a whole different part of the computer to make the addresses go over there and reference that area instead of the ROM. So that's how you kind of bank switch and get more memory for your system. So within that RAM, this goes even into more detail, again, from the manual. So within that RAM itself, there's different sections that they have reserved. So at the very bottom there, you can see reserved pages. There's something in this processor called zero-page memory. It's a faster access and takes less bytes to reference it. So those are usually reserved for temporary variables or something you need to access a lot. And then the Apple II designers decided that there's going to be some graphics buffers, some low-resolution graphics buffers at the bottom, and then some high-resolution display graphics buffers up there. And you can see that little white area right above page 2 on the low resolution. That's that stack area that you don't want to be messing with because the processor uses that area itself. All right, so that's a little bit about the 6502. So I'm going to tell you how to talk like a computer. And some of this may be like very elementary to some of you. Some of it's maybe new. To me, a lot of it was kind of new. So binary, ones and zeros. So we count in base 10, 0 through 9. as our digits. Binary only has 2 digits, zeros and ones. Most of you know this. So then we decided that's kind of hard to count large numbers in just zeros and ones. So people were like, well, let's come up with a system where we have 16 characters that represent a single number instead of just 2 or 10. And so that's why we have hexadecimal, it's 0 through 9, and then the characters A through F. So you can get 16 characters in there. So if we wanted to represent the number 13 in binary, that's 1101. And you can count that up by saying we have 1 8's worth, and then we have 1 4's worth, we have 0 2's worth, and we have 1 1's worth. So we add those up, that's 13. And so in hex, we would call that 0xd, or just d, really. In Elixir and a lot of other languages, you reference hexadecimal numbers with the 0x in front of it. And so that's d. So if we wanted to go further, this is an 8-bit number, so 180. And this is how we'd reference it, or how we'd write it out in binary, and also in hex is b4. And then if we go to 16 bits, it gets a little unwieldy. Like that's a lot of bits that you have to say, oh yeah, that's 62,954. But some people who are used to writing stuff in hexadecimal and some of these different, well, especially in this era, they see F5EA and they start to, it becomes almost second nature to some of these people who have done this a lot. So that anyway, F5EA is much easier to write than all those ones and zeros. So all those ones and zeros really are telling the computer, like I knew, as a computer program, I knew that everything's ones and zeros, right? That's kind of, you know that. But it's like, well, what are those ones and zeros actually doing? And really, it's turning on and off parts of the computer's brain. So those ones and zeros can be connected to these inputs and outputs of the chip itself. So if you see, let me see the next slide. So that's the chip up there. You can see that has those little feet. And those are just inputs and outputs, ways that the chip can communicate outside of itself. And on this slide, this is the kind of the internal diagram of the chip itself from the original manufacturer. And you can see all those little arrows pointing out of that main area, that instruction decode area. And those are just, we can just think of those as different parts of its brain. And those ones and zeros light up different parts of its brain depending on what you want the chip to do. So for example, that top left one, or kind of the middle there, the index register. So if you needed to turn on the index register Y or give that index register an instruction, then it might light up that line out of the chip to the index register Y and say, hey, be ready for the next instruction because I want you to record it or something like that. So those ones and zeros are really turning on and off parts of the computer's brain. And that's something I didn't really fully understand until I started diving deep into this, really. OK, so that's ones and zeros. Computers talk ones and zeros, but as humans, we don't talk ones and zeros very well. So if we wanted to program this computer to turn on and off parts of its brain, this is what we'd have to do. So in order to load the number 241 into the accumulator, for example, let's say we have some programming task we need to do that this is vital. What we need to tell the processor is 10101001. That's load into the accumulator. And then 241 is 11110001. And as you can imagine, that gets a little tedious to know that load into the accumulator is that left, I'm not even going to repeat it, that left binary sequence. That can get kind of old. And we can't recognize that very easily. And so we can shorten that to hex A9, hex F1, which A9, again, is the 10101001. And then F1 is 241. I was talking to Jim Fries, who kind of organized the conference at the speaker dinner, and he grew up like programming these things. And he had all the opcodes memorized, which is awesome. Like he would see A9, he's like, I know exactly what that is, which is awesome. So most of us don't know what A9 is, so we decided that LDA would be a good way to kind of make that make more sense to us. So load accumulator, so LDA, kind of a mnemonic that we can use to remember what we want that processor to do. What an assembler does, so that's the assembly language, is LDA and then the hash 241. That's an immediate addressing mode. It basically says take this literal number 241, put it into the accumulator. And the assembler takes that line and then moves up the line, essentially, to those ones and zeros. And that's what's fed to the processor to turn on the right parts of the brain in order to load 241 into the accumulator. And I mentioned all those opcodes. This is like a cheat sheet I found from back in the day, probably in the mid-'80s. But you can see that main area there. Those are all the different opcodes that this processor has. And it's kind of like a cool, I don't know, table reference area. Here's a closer look at it. And it's got some other things about what happens to the flags on specific operations. But this is something that in the early days before assemblers, someone would take like handwritten assembly and change those with something like this into those ones and zeros and put that into a computing system. And so if you think of punch cards are either punched or unpunched, and those are ones and zeros. So you would take load A in the accumulator or load A241, punch out the right numbers for that, and slide that into the computer. I don't think 6502 actually ever had a punch card system, but that's the same idea of like very old punch card type systems. You just change what you wanted to do, turn on the right parts of the brain of the system through those punches, and then off it goes. Oh yeah, I forgot. There's just more information on here, like different addressing modes, the ASCII character set in case you need that, what the pins are of the actual chip, that little conversion chart over there. Just helpful things for the programmer to use during their time with the chip. All right, to the code. So we've gone through 6502. Hopefully you get a little bit more of an understanding of what I'm trying to do here, or at least the system that is being modeled or emulated. So in my code, I have an x6502.cpu module. And this basically handles the processor itself. So it contains registers, it contains the program counter, and processor flags. And it's really just a struct here. You can see I just kind of reset them to sane values at the beginning as default. So the accumulator has 0, X and Y registers. The stack pointer is referenced as FF. The processor flags and also the program counter is just set to the reset vector. And so I mentioned that the reset, there's like that part of address that is reserved for vectors. That is one of those. It's the reset vector, so it's FFFC. And essentially, when the processor turns on, it goes directly to that memory address and says, give me another memory address, the 2 bits or two bytes of memory. It says, where do you want me to start the program? Where should I go to look for the beginning of the program? And so that's what the reset vector is. So you put in your memory where you want your actual program to go. And so that's what the reset vector is. Same thing with interrupts. If an interrupt is handled, you can cause interrupts to, like, I don't know, sensors or any other sort of I/O. Then it'll also go to a specific interrupt vector and say, OK, where do you want me to go in this situation in your code? And then also I've got flags. Those are just the location in the byte, which bit in the byte has that particular flag. So there's like overflows, zeros, interrupts are enabled or disabled. There's like a decimal mode in case you don't want to do hex conversions of your own, things like that. All right, so then above the CPU, I also have the idea of a computer. And I'm still not sure that's the right name for this idea. But this module contains the internals beyond the 6502 itself. So I wanted to model the memory, the actual buses that it communicates on, the connections like input, output, and of course the state of the CPU itself, whether it's running or not. And since this was a learning exercise for me, I wanted to kind of model all those little pieces of its brain as possible. Well, not as possible. At some point, it's like each piece can get a little tedious to model that. But I did want to model the address bus and the data bus. And those are like the address bus is 16 bits and the data bus is 8 bits. And I wanted to model those to where when the processor decided what it wanted to do next, it would have to actually look on that bus to see what it should do. So we have, in this struct, we have break, whether the break state. We have a CPU, what CPU it actually holds, a cycle count, which actually isn't implemented at this point. The memory that it has is just a list. The address bus, again, reset to a sane default, as well as the data bus. A running state, and then I/O subscribers, which we'll get into a little bit later. All right, so when you initialize the computer, you can pass in a memory list of your own if you wanted to, or just, again, defaults to a sane default of 64K of memory, all initialized with zeros, I believe it is. And then it resets the computer, which basically means it puts all those accumulators to 0, resets the stack pointer to FF, and goes to the reset vector that the processor automatically goes to on reset. So on every, well, not maybe not on every, but in most CPUs that I know of, there's like a 3-step cycle that it goes through to actually run. The first is it fetches the next instruction, and then it decodes that instruction, and then it executes the instruction. It could be destruction. The instruction of destruction. So I wanted to model those steps as well. And so here's kind of how, if you wanted to step the processor, it goes through these particular steps in order. So first, it just makes sure the processor is not in a break state anymore. Then it puts the program counter on the address bus. It handles any interrupts that may be on the data bus or on the address bus. Then it updates the data bus from the address bus. We'll go over some of these in more detail momentarily. And then it steps the program counter to the next location, and then it tells the CPU to execute the instruction. So put PC on address bus, that's pretty self-explanatory. All it does is whatever the program counter is, it transfers that value, which again is 16 bits, onto the address bus. And so it just says, hey, this is the program counter. It's now going onto the address bus. And later on, things are going to reference that address bus to know what to do next. All right, so let's look at handle interrupt location. So if on that address bus, the program counter, or the program counter is in one of those interrupt locations, then it simply does what I mentioned earlier. It looks at the next, the 16 bytes of memory that are in that address location, and then puts the program counter to that new address location, and then breaks the processor, puts the processor in a break state. And of course, if the processor is not in one of those interrupt vector locations, then it just passes it on through to the next step. So another part of the fetch cycle is updating the data bus from the address bus. And this really just takes that address bus and says, where do you want me to look for the data to know what I need to do? And so it goes to memory, gets that address from the memory, and then puts that into the data bus. Just transfers that over. And again, that's 8 bits of data. So what 8 bits of data are at this location in memory? And this is just, again, how the steps go through, because now we're about to leave the computer and go to the CPU. So step PC is pretty self-explanatory, just increases the program counter. And then, so we're going to head over to execute instruction. Now, I mentioned that there's 3 cycles, typically. There's the fetch, decode, and execute. And Elixir made it too easy to combine 2 of those at the same time. So decode and execute are really kind of combined because of pattern matching. I guess you can call the pattern match the decode step. But the first thing it does is if the computer is in a break state, then it just passes it on through and doesn't execute anything. However, if it's not, it just passes it on to what I call the executor. So let's look at the executor. So the executor is a decently long file because it defines each of the opcodes in every operation, and then has a pattern-matched execute function that passes it on to a specific module to handle that execute function. So in this case, all the different ways to do AND on this processor are those hex codes up there. So those are the different opcodes for AND. And so if we pattern match here, so when the opcode is in those AND codes, we're going to pass that to the executor AND module and tell that to do the execution. And so even with there, you can imagine that since we have all those different AND codes, like all those are different ways to do AND, you're going to need the executor in the AND function, or sorry, in the AND module to also do some pattern matching. So this is more of the decode step. So this is some module documentation for that AND module. It's a little small, and apologies about that. In an interesting twist, unlike most projects, the documentation in this project got better as it went along. So this is a good example of documentation, but it basically says what the processor is expected to do with these AND codes. So you can see it's going to AND the adder, which is the accumulator, and a memory location, or a value. So then there's this table here that has the different addressing modes. We won't go into all the different addressing modes here, but there's different ways that you can say what to AND with the accumulator, and then how the assembler would interpret that, or how you would write that out in assembler, and then which opcode that is in hex, and then how many bytes it takes to store that information, in case you really needed to optimize for a small program, and then, of course, how many cycles it takes on the CPU itself to execute those instructions, and then what it does to the flags as well. So here's an example of ANDing with an immediate value. So earlier in that example where I loaded an accumulator with the value, there was that, that hash or the pound sign and then 241. That's basically the immediate value. It's like literally this number is what I want you to AND with. And so this is the function that handles that. So we pattern match on the 29 hex, which is again is that AND immediate value, and we put the next byte on the computer onto the data bus. So remember, the program counter has been stepped past the operation, and now it has another address location. And so it's going to take the next byte in memory and put that on the data bus and match that into our new computer and have our data bus have that new value. So whatever came after that opcode 29 in our memory is going to be the data we need to put onto the data bus, that byte we need to put on the data bus. Which we do that, then we AND it with the accumulator in the CPU as our new result. And then we store that result as the new value of the accumulator and set the appropriate flags in that set flags function, which actually don't have an example of that set flags function, but the source is online. You can take a look at that if you want. All right, so what I want to make sure is like the idea of the data bus and the address bus are maintained. So it's not just pulling it directly from memory, but the buses are actually in play. So it takes that value and puts it onto the bus. Again, that was important to me. Probably most emulators are like, don't even bother. So the put next byte on data bus is pretty self-explanatory. Basically, just a small utility function. Just get that location of memory that the program counter is at, put it on the data bus, and then step the program counter again to the next one. All right, here's another example of ANDing from that module. And this one is hex code 3.1. And this is the 0-page indirect Y-indexed version of memory addressing. And again, I'm not going to get into that, but it's pretty cool. Like some of this stuff, I was like, oh, that's why arrays are 0-indexed in sane languages. It's because of stuff like this. So in this case, we're going to put the 0-page on the address bus. And I mentioned earlier that 0-page addressing is kind of a faster and more efficient way that this processor can access data. So as you would expect, we get that data, put it on the data bus, and then use that, AND it with the accumulator, store it as the new value in the accumulator, and then set the flags accordingly. So it takes a little bit more processing time to do those steps as just ANDing an immediate value, but gets what you need done. All right, here's put 0-page on the address bus. You can see it, again, it's pretty self-explanatory. It just grabs that location in memory, offset by that Y index register, so that index. So in this case, that's why it's zero-based indexing, is because the array is going to start in this part of memory, and we need to offset it by this many bytes. And it's easier to write that in assembly as one instruction instead of saying, if it's 0, then do it this way, and if it's 1, do it this other way. Instead, just do it always that way and increase that Y register to index it past the 0 point. Anyway, that's something I learned. That was pretty cool. All right, so memory, this is different addressing modes. I'm not going to go too deep into details here, but these are the different ways that memory can be addressed. There's indirect and there's absolute. Indirect basically says what's in this particular address location, and then it goes and looks for that address location and says what's the data there. And then absolute, this is what it sounds like. It's like what's at this exact address location. All right, so above that, so we got the CPU, we have the computer, we have memory, and then I wanted a computer server. So everything it's like a gen server that holds those pieces of information that I can then interact with. And there's a couple of important ideas in here. One is I/O subscribers, and that's, we'll get into that here in a second as I show you kind of the web interface I created. And the other is send I/O. So which part of memory address do I want to send data to? And I/O subscribers is sending data from. So that essentially, since this is an emulation, we can have all the memory we want, really, and all the emulated inputs and outputs we want. And I needed some way to send inputs and outputs from the processor into another part of the system. So these I/O subscribers are kind of that idea. All right, so we're past X6502. So then I was like, cool, I have a processor now that I've emulated. What can I do with it? And that was the whole idea of the project from the beginning for me, is I wanted something that was flexible and not just an Apple II emulator. It wasn't a Commodore 64 emulator. It was this processor emulator. Then I could build my own system around it to do whatever I wanted it to do. In this case, I was like, well, shoot, Phoenix LiveView is pretty cool. I'll do it in Phoenix LiveView because I can build a more complex computer, a more complete computer around this processor. I can monitor what's happening in memory as I'm learning what these opcodes do. I can practice my assembly language programming, emulate hardware input and output with like a quote-unquote screen, and then see it all happen in real time with LiveView. So this is from Page Live, just the default name. I was like, shoot, I'm not going to be creative with it. So it initializes a computer and then loads a file. In this case, the file I'm running that I showed in the demo is just an ElixirConf assembly language program I wrote and then compiled to just the ones and zeros. So load that file up, reset the computer so it's has that reset vector and it gets it to the right state of where I want the program to start. And then it starts the link and adds that to the state of this Page Live component. I also subscribe to the computer server. So anytime the computer updates, it's going to let me know about it. So I can either update the memory address locations or update those registers as they need to be. And then also I/O subscribe. So you can see here that I have a range of addresses. In this case, it's just one address. But I want to know specifically when those address locations change. So I mentioned earlier that as a program designer, you can choose what parts of addresses you want to use for whatever you want, whether it's RAM or ROM or input-output. In this case, me as the computer designer decided that I want FFF0 to represent a byte of data to represent a character that I want to output on my screen. And so I was like, cool, I'll make that my I/O, my way to communicate from the processor and my program on my processor to communicate to my LiveView component. So anytime FFF0 changes on my computer, let my LiveView component know about it, and I'm going to do something about it later. And then, of course, I just set the state in the socket with the computer, my computer out, which is my quote-unquote screen, just a string at this point. Like my PID, my show displays, just whether or not the displays are updating in real time, because if I run this full speed, it slows it down quite a bit if I try to update all the time. And then the memory dump itself from the computer, and then some other stuff that I put up there for debugging. All right, so then one thing I didn't show on the demo that I meant to do, I forgot to do, but I'll show you again later, is handling input. So as I type keys in the LiveView, I have a hook from Phoenix in there to say every time I press a key, send it to me, and I'm going to handle it here. So I'm going to basically match it against the ASCII list, which is defined up in the top of the file. You can imagine what that is. And I'm going to decode that into its binary representation and send that directly to my computer server, which handles the computer. In this case, again, as the computer designer, I decided that my computer is going to receive input from the outside world at address FFF1 hex. And so I say, all right, LiveView, send this byte of data, which represents my ASCII character, to my processor and let my program on my processor handle that information. And then as you can see, I don't do anything with the screen, which is going to become important later. So I don't do anything other than sending that data to my computer server. Now what my computer server does, my program actually does, is it listens for that in a loop, which again I'll show you in a minute. It says, hey, is there new information yet? New information yet? It says, oh, now there's data in this memory location. I know what to do now. So all it does is basically mirror that to FFF0, which, if you remember, was my output directory, or output memory location that my LiveView component was listening for. So it's really just going to echo back any character I type in, but instead of doing it within LiveView itself, it's going through my CPU and my assembly language program that's actually doing all that. So all I'm doing is decoding that value back into an ASCII character and passing that, or appending that to my computer output, my screen. All right, so now that you know all that stuff, let me show you the demo again. Oh, there it is, nice. And as you can see, let me get I hate having to do this with two screens. Actually, let me do this. Let me turn off mirroring, or turn on mirroring, so I can see it as well. I'm not to look over my shoulder the whole time. Okay, cool. So you can see here, this is my memory dump on the right, and I mentioned that reset vector is at the very bottom here. It's 5000. Now, this processor is in what's known as little endian, so it takes the small, the least significant byte first in memory, and then the most significant byte. So this should be read. It's stored as 5000 hex, but it's going to be read as 0050 hex. So this is the reset vector telling the computer, hey, whenever you reset, I want you to go to address 50 in memory. And so you can see up here, actually, that's going to take forever. Go up here to 50. You can see this is the first real piece of data I have in memory, and that's where the program actually starts. And you see the program counter here is at 50, and I wrote a disassembler as well that basically turns those hex values into what you would typically write in assembly language. So we can see here that value, or that opcode, is saying load X, and then 00 is the next byte, load 00 into X. Actually, it's the hex value 00, which is still 00. So if I step this, you can see it goes to the next, since that instruction takes 2 bytes, then it goes to, the program counter goes to 52, and you can see here that this decodes to load into the accumulator a value at memory address 90 offset by the X register. And so you can see here the X register is at 0, so it's going to be memory address 45, and we're going to load the accumulator with that value. So if you see at the top here, this accumulator should, if I step, now had the value of 45. So we loaded that value into the accumulator. Program counter step to the next thing. It's saying branch if a specific thing is true. In this case, it is true, so it's going to jump to a subroutine, which I've made as my input-output. And all this subroutine does is it stores whatever's in the A register in memory address FFF0. If you remember, that is what I just declared was the output from my processor that my LiveView is listening for. So when I step this, we should see E come through, which is hex value at 45. So all that's done is the CPU has said store 45 in memory address FFF0, which is here now. And now my LiveView has decoded that into the ASCII value E and decided that's going to be part of the display output. So I'm going to just run this so you can see things happening. And you can see that it's just going to type out that initial thing we had at the beginning. But you can see all the different values change. Like the stack pointer jumps back and forth as I'm jumping to that subroutine and back. The processor flags aren't really updating much. I'm not doing many operations other than moving data around. But you can see also like this memory address is changing as the new values are coming through to be displayed and all that. So look back here to the stack. Let's get to the stack. So like right top of the stack. So it should be right around here. Right there. So here's the stack pointer. Oh, we're off the stack now. So now we're in this endless loop that I told you about, where it's like, hey, now I'm listening, because I have a prompt. My program is listening for anything at that memory address FFF1. So let me go all the way back down here to FFF1. So there's nothing in there. So it's saying if there's a 0 in this memory location, just loop back and listen again. So you can see if I press a key, J, then it found that memory location and updated the output. Let me stop this. Okay, so I'm going to press the button now that it stopped, like L. So Phoenix still sent that to my computer, but my computer hasn't run the instruction yet to know what to do with that. So if I step it, you can see now 6C is in that memory location that's my input. I'm going to step through it again. It's going to jump to that subroutine that outputs it. So it's going to store that to my output location, return from the subroutine. Now it's going to load X back to the 0, 0. And then it's going to store FFF1 from the value of X, which is basically going to reset it back to 0. And there it goes. And then we just do the whole thing over again. Compare it and compare. Also, just kind of fun. I was like, well, it's kind of a boring OS. What if I did something a little bit fun? So I did an exclamation point. So it's listening for an exclamation point. If I type that, it's going to type a special little greeting. And so that's basically the ElixirConf OS that I wrote specifically for this presentation. All right, let me stop that. All right, so there's still some things I'd love to do with this. One is make it run at a correct speed. For example, the original ones would run like 1 megahertz. Modern ones can run up to like 4 megahertz or maybe even further. So I'd love to be able to do that on like the millisecond intervals location or precision. And I'm not exactly sure how to do that quite yet. Also, cycle correct execution. So some of those commands take longer or more cycles to execute for the original processor. I'd love for that to be emulated as well. And also, maybe more examples of like full computer systems. Like take that memory map from the Apple II, for example, and use that as my computer, and then find the ROM from the original Apple II and put that as the memory and see what happens. So here's some references if you're interested more in the 6502. I got a lot of the documentation from these places, so if you want more information, go here. Also, Ben Eater is he's on YouTube. He basically builds a computer from from the transistors itself. Hold on one second. So you can go from knowing like what a transistor does to actually building a full computer around it, and it's amazing. But he also builds a computer around a 6502 itself. That's kind of his new thing this season that he started after I did this. So I was like, okay, cool, this is going to be fun. Do you have a question? Oh, thank you. Yes. Yes. I have not considered that, but that is very interesting. Yeah, that'd be cool. Yeah, yes. Yes, well, as I mentioned in the introduction, I don't know, since you're standing, you may not have heard that, but that was what led me here to the first place, was I want to learn what assembly is and how to do it. And this was what led me to this processor itself, because it had more of a reduced instruction set. So it's very possible that someone could take something like this and create a course around it. I know there is, I don't know if it's on here. I think there's something called Easy 6502 that may have a bit of a course around this. It's web-based, and that's maybe something to check out if you're interested in that. Yeah. Oh, thank you. Thank you. Thanks. Anyway, I wrote a book, Phoenix in Action. Go check it out. There's a coupon code for you if you want to get a little discount. I'm on Twitter and GitHub at Geo Lessel. This is actually live now at Geo Lessel X6502. Please go look at it, make it better. I've got a bunch of to-dos in there and some references, so please take a look at that. And then I'm on the Slack and Elixir forums as Geo. So again, thank you so much. Let me know if you have any other questions.